Today? There we go. Okay, a little delay there. Little delay. Let's get it. Come on. We're in the final stretch. And, obviously, before we jump into it, I will go ahead and, address the Connect 4 on the board. So this is just it's a little thing. Again, like I was saying before, kind of we started. So this is mostly just for open house last semester or last year. All I did was I took the 411, submissions from Connect 4, and I, finagled the visualized simulation. So it's just a randomly selected pair. And then when the game is over, I select a new pair and just fight again. So funny enough, some of y'all crash the stuff, so I know y'all didn't really test your submissions that well. But no, so, again, this is just something that you can technically do. And enough people are already trying to figure out, what number you are. I'll say that there's 120 of you, and so, depending on your section, I'll say that, right? If you're on the later stage of names, what am I doing? I think it's contingent on both of them, but obviously, I can't remember if it's first or last. I don't remember how Moodle structured it, but you might be able to rough estimate. Someone is I'm about that level. But no, so again, this is what you can do with AI. It's really wild and really fun. But now that fun part has warmed your heart, you wonder who you are, now I have to break your spirits. Where are you? Because that's not it. You have a lecture exercise being released this week as well. So be mindful. You've got your problem set and you got a lecture exercise coming at you next Monday. So, look at your weekends. But the entire idea is we're going to spend today talking about this because it's sort of the last final hurrah before we introduce the machine learning section. The big idea here is, and just like we'll see, what happens when you do a bunch of probability, but it's now contingent on something else. Probability beforehand, as we're talking, was independent, right? Now, what if it isn't? And so, with that out of the way, since again, it's what we're talking about today, I'll jump right on into it. So, like I said, right, we are in the final stretch. What are we, week 12 now, right? Is that close? Does that sound eerily similar? We're starting, we're hitting the ending point, but sort of as we're moving into our next section of machine learning, Bayesian Networks serves as essentially this was the pinnacle of AI before the neural network took over. This is the area of this is what people were doing up until about 20 years ago, when neural networks, started really picking up, because again, we were looking at this notion of uncertainty. We were utilizing probability to make effective decisions based on our observed evidence. And so it's been a hot minute, right? Last week, y'all had a midterm, and so, you saw this, and all you remember is you need to do a math equation real fast. So a little bit of a refresher, right? That notion of the probability, the full joint distribution table, right? The entire idea is every single one of the variables that you might be having floating in space that you're working off of in your analysis kind of or world. The big idea is, right, if I mapped out every possible value for every possible variable, I'm going to get some kind of distribution of the probability of these things happening. Again, you take this from observations, and there's an entire section that we don't go into in this class on essentially trying to build your Bayesian networks, right? We're going to assume it's already been created, but that's research in itself, like trying to build one from scratch. But again, we have this notion that, with all my variables, oh yeah, it is on there. With all my variables, I have, again, this sort of here's how, likely a particular combination of those values is. So here's one of the problems though, right? Think about just most of the problems when it comes to computer science. It almost always boils back down to the notion of scale, right? I showed you 3 variables because 3 variables fits nicely on a PowerPoint slide and it can represent things. But what happens when I start to add more variables, right? The second I add this, D variable, it goes up by 2, right? We double the number of possible configurations is what I'm trying to get at. So this went from 8 to 16. If I try and add just a 5th variable, only 5 variables, right? 2 to the 5th power, 32 magically. Still not bad, right? But one, again, visually that gets annoying. 32, fine. What happens as I keep going, right? Again, you've learned the power of 2 and the whole binary structure. The second I just try and do something like, 2 to the power of 10, right? What is that? 2, 4, 8, 16, 32, 64, 128, 256. Okay, that's 512. That's still pretty small, right? 32 bits, right? 2 to the power of 32. That's 4 billion, and that's for 32 variables. That's still a very small number. And so that's where we start to kind of run into the limitation of just a probability table by itself, right? Again, we're going to sort of find a resolution to this in a second, but for right now, the big issue is we have a brute force. We have an exhaustive search that we have to do if we're trying to, utilize these things. It's kind of, slow. So the other kind of major issue here is the probability table by itself doesn't really address some of the facts of specifically influence, right? This is Statistics 101, right? You learned about something called independence. What's independence mean? Let's say it loud, proud. Not related or dependent on another event, right? If I have a variable and I say that variable is independent, A is independent of B, then the big issue there, or not the big issue, but the big idea there is, well, it doesn't matter what the value of A is, it will have no impact on what the value of B is. But you all know, right, from just real life, that's not really how a lot of our variables work, right? There is some direct influence going on there. And so the idea becomes, as we start to get back into that notion of, conditional probability, right? The idea is I have some piece of evidence that I have observed. These are the things that I do know about the world. And so now what I'm trying to do is I'm trying to, answer that question. How likely is A to happen given that I have observed B, right? This is from the midterm, so it's a little bit of, hopefully a refresher. But again, that notion is, right, sometimes these variables can become, now it's a matter of, well, now that I observed something, how, impactful was it to my other variable, right? Given the observation that I stepped on a crack, how likely is it that I've broken my mother's back? That's right. Yes, thank you. But okay, you all understand. That's a nice little kind of, it's not a nursery rhyme. It's just like a saying, right? I don't know if it's an idiom. That's I don't know. I could take, either way, my point being is we all understand that that's not a true statement, right? That's not how it works. We all, have in our brains this notion of I got to step on the crack, but that becomes its own little thing, right? Again, if we're thinking about it from a conditional probability perspective without thinking Bayesian networks for just a second, right? What happens? Well, if I do focus in on this notion of, again, I have two things. I have an observation and I have a question. right? So the A, B, kind of, what's the probability of A given B? What's the probability of backache given step on crack? Well, the big idea, right, is that what I need to do is I need to find out the probability of my observation, my evidence. How likely is just what I do know about the world? This thing. Then, this is where, almost very similar to your logic resolution, right? We make an assumption. That was what proof by contradiction did, right? We were saying, let me just assume the opposite and let's play things out. I'm doing that same thing here. I'm saying, well, okay, how likely is it that you step on a crack? Then let's make an assumption that your back, my mother's, poor back is broken. Well, how likely is it that these two things happen, at the same time? Again, this is stuff that you did, so it's a little bit of a refresher. I'm just sort of connecting the dots, because when we think about independence, right, the big idea here when we talk about that, it's not just, these two variables don't have an influence, but what we mean from that, from a mathematical standpoint, right, is, right, now that I have this idea, independence can allow me to have a very simple approach, right? If the variables are independent of each other, and I'm asking that question of just likelihoodness, right? Then, if I ask just what's the probability of backache, injury, step on a crack, again, assuming that these are all independent of each other, well, then that's just a very simple, I take the probability of one of them and multiply it by the probability of sort of the rest. But the problem is, we understand that, again, that's independence. We're talking about this now where maybe they have influence over each other. Again, we know that this one's false, but we have examples of this that we've seen in the past. Toothaches, cavities and whatnot. And so, as we're looking at the notion of independence, right? Again, as we think about what variables are doing when they are independent, I have this giant universe of 3 variables going on here. If I want to say that something is independent, what ends up happening is, again, we have that notion that, hey, A and B, what's the probability of both these things being the value that they are? Okay, that equals simple multiplication. Again, no different than what we've seen in the past. But, again, thinking about it from independence perspective, what's the probability of A given that I have seen B? What's the probability of B given that I have seen A? If 2 variables are independent, then what we're going to end up seeing is that the probability of A shouldn't change, right? Just because I know what B is should not change the influence here. That's what we talk about when we mean independent of each other. Same thing. Again, if I know A, but that's the only thing I know, right, it should have no influence on B whatsoever. That a little bit of a refresher. Again, don't give me that look. I've seen students, the mind is blown when I do a refresher. So again, there's that blah, blue. So what happens? Why do I kind of start to finagle this? Because this expands, right? Now, if I add in additional variables, right, I'm just dealing with now this notion of it's more observations or more assumptions coming into play. Independence can still exist, right? This kicks in. The probability of A given I've seen B and C will be the same as just the probability of A given C, right? I don't have, that's again this notion of independent of each other. B is independent of A in my little toy example here because you can see that with it or without it, I'm going to get the same value. And that's the key part. With it or without it. Think about what we do in this, career field. We do math on this thing. Math takes time. I don't want to take time, right? Y'all want to do things now, instantly, blah, blah, blah. Y'all want to know what your student robot number is already. Right? Why can't I know this answer now? that same kind of concept's going on here, right? That's what we mean when we talk about independence. We don't need to do a calculation. That leads now into what we call the Bayesian network. This was, like I said at the start, this is what served as the foundation of modern AI before sort of the push of the neural network, which we'll talk about. Again, we're going to get there. We're going to get there. You'll learn how ChatGPT works later. Right? I got to give you the full world of AI, and that's, again, what happened was, hey, we have data being produced all of a sudden, right? Think, again, we got to go back. When I was a child, 95, the internet was just getting installed into homes, kind of things. That means we were just starting to log data in networks and things, right? We were just starting to do these things. Well, the world kind of realized, hey, with the surplus of observations, maybe I can produce some probability networks that will allow me to identify things. And again, the Bayesian network still in use, right? That it is still used. It is commonly used. What is it? Bayesian classifiers, what it gets often referred to as well. But the big idea is, again, everything that you see here, right? Each one of these, hey, is something spam? Well, what's the probability given what its text is? And we'll actually see that in our NLP section, speech recognition, right? When I say the word call mom, right, what's the probability that the sound that you just heard was the word call? What's the probability, well, of diagnostic systems? What's the probability? I'm skipping over robotics. Medical application, same kind of thing. What's the probability of a certain medical condition given your symptoms, your observed symptoms, right? This is where we start to really see a lot of the power in this Bayesian network. Now, how does it start to get structured? And it's one of your favorite data structures all over again. I warned you that we are just applying everything that you've learned in all your other classes. Welcome back to 316, ladies and gentlemen. It's the DAG. The directed acyclic graph, the entire idea, right? This is a directed graph that you can't form any kind of cycles to, right? We all sort of understand that kind of notion. You've seen this graphic or a similar one in your lifetime, hopefully by now. Otherwise, I got to talk to Dr. King, right? But the big idea is, again, when we start to think about these different nodes, right? Again, it's just, think about it like it's no different than another variable. It's just one of the variables in space. But here's, again, this notion of what happens when my variables influence each other, right? Again, probability works nicely when everything's independent, right? I just do multiplication. Sometimes I do a minus. That's it. But what happens when a variable has a line attached to another variable, right? The Bayesian network, what it means and what we kind of use for this is to talk about this notion of influence, right? There it is. So when we see this, again, what we're saying here is that variable A has influence on variable B. Variable B has influence on C. Variable B also has influence on D. Indirectly, A has influence on D. Okay? Okay, all right. So we're okay. We're refreshing our brains a little bit. Again, the A is the ancestor if we're thinking about it from 316 terms. Excuse me. We're talking about it from a probabilistic standpoint. So whatever A ends up being will have an influence on what D turns out to be because, again, there's that arrow going through it. So that's where we start to see, again, when I think visually trying to represent when something has influence versus does not have influence, right? Stepping on a crack. We all have acknowledged that that's just a saying. I guess it is an idiom now that I think about it. Superstition, I like that term, right? This kind of thing has no impact on the real world of a backache. But what does? Okay, well, if you do have some kind of injury, maybe pre-existing condition, long-standing injury from when you were a child, all of these types of things. I got hit by a truck, now 24 years ago? It's okay, I lived, right? I got hit by a truck. Why I kind of present that is like, again, I had a lot of surgeries done. Well, that helps, but it's a long-standing injury. So what's going to happen? Well, the influence of just like this piece of work does mean that my gait is going to start, wear and tearing. I'm starting to get older. So, it's starting to break down. Well, that injury that I had 24 years ago, I recovered from it, but ever so slightly, right? My gait changed. My walk changed. Oh, look at that. You wouldn't even know I had any problems, except for, you notice how I'm doing this all the time, right? Stretching. I know, if you can't see, I'm stretching before class. Why? Because I got hit by it, right? But no, what's that going to cause? Well, those long-standing, that slight adjustment in gait over a 20-year cycle is what would cause something like knee problems or a backache. This is why if you work a very strenuous position over the years, right, you just get wear and tear. Your shoulders break down, your legs, your back, all of these things. That's where we start to, again, see this idea of influence. Not stepping on a crack, getting hit by vehicles. My point being is, okay, now that we have this idea of there is an influence, how we calculate out the probability changes. What we end up doing is, again, now we start building multiple probability tables. You're no longer dealing with one giant one that is mapped to everything. Instead, you only worry specifically about your parents. This is going to be something that, take a second, process what you're hearing here. The only thing I care about are my parents. The only thing B has to care about. Right now, there's only one other variable, and it's called A. But what happens when there are more variables, right? When I get back to this idea of something like this. Yeah. You will have a specific structure that, because I am dropping a section, so I'm wanting to, you are not going to have any situations where a parent is not an influence, if that makes sense. Or we'll talk about it, if that makes better. I will spend a little bit. You will have both, actually, now that I think about it. Your lecture exercise is both. Yes. So you will have mom and dad, right? But the big idea is, again, if we thought about it from that joint probability table, that distribution, way too many variables, too big of a file. What happens if I instead only include or only look at things that do have an influence on me? Now I don't need to worry about like some E variable that also exists. Because again, does it influence B? No? Okay, well, I don't care, right? What that turns into is, again, right, if a node does not have a parent, right? A has no parents, has nothing influencing it. Again, we're in a small little universe here, right? Hey, it just has its own values, right? There's a 60% chance A is false. There's a 40% chance A is true. Okay, well, what happens to B? Well, B has a parent, has something influencing it. So not only do I look at my B variable, right, but I also look at my parent variable. And I'm just referring to it as one, but you can see then there's its own mappings that go on here. I want you to kind of take note of something. What's something odd about this probability table? It doesn't add up to 1. We'll see, I got a picture here in a second, but I do want you to kind of be mindful of that. Correct. And yes is the answer, if that makes any help. Yes. Now, that's just to keep on expanding. Like, this is where what happens if I do happen to have more children, right? Same kind of concept. C, when I talked about parent, I only talked about parent. I don't care about my grandparents. Yeah, I know. Rough. You know, they fought hard to get here and establish a life for me, and I just don't care about them. Love my grandfather. He wrote a book called I Love America. Same?
No. Oh, no, I meant
Oh, no, I care about mine.
Oh, sorry.
Anyways, all right. My point being, right? My point being is, again, what we're talking about here is, again, if we look at D, right, what do I need to model? Well, I need to model the value of D. I need to model the parents' values of D. But that's it. I don't care about anything that is not directly influencing me when I'm building out the Bayesian network, right? There are steps where you start to kind of use your grandparents, and you look through pathways. But for just like the probability calculation, only thing I need to list is my parent. Well, why? Because, again, think about it from the influence chain, right? Well, D is influenced by B. B is influenced by A. So I already have that in place elsewhere, right? So I don't need to worry about it, or I don't need to map that A value for my D probabilities anymore. This is where, right, when we think about the calculations, right, I showed with the joint probability distribution, yes, if I go in and did the math on the joint probability table, everything should have been equaling to 1, right? That was my universe. But this doesn't seem to be doing that. In fact, it's seeming to calculate out to the number of variables suddenly, right? There's one variable. One. There's two variables. Two variables. And here's where it's, a little fun. If you were to map these out, so, how I work, I like to have builders that way make my life a little easier. Where are you? Bayesian network. There's my Bayesian network. My download. I'm going to pause for a second because I don't need y'all seeing the final exam. I mean, hey, this is how I do the calculations, right? So if we're looking at that network, right? If we see, again, here's that same structure. Here's that same, right, 60% chance false on the A, the 99s, mappings of each one of these. If I were to take this and run the calculations, wouldn't you know it? Again, hey, look, there's those A's being true. There's those A's being false. Here's the BC combination. You can see I'm doing weird fancy stuff. But there's our calculation. So we are still getting the 1, but not in how we're presenting the data. If that makes sense. Does that make a little? Okay, good. Something to be, I've had questions in the past of like, why doesn't this equal 1? It does, just not in this view. Right? So why we kind of focus on this, why I spend so much time on this, is because this brings up a big fancy $5 word that essentially spearheads the rest of AI or modern AI, machine learning, speech recognition, all of these things that we start looking at as like modern AI. It is known as the Markov condition. The only thing I'm looking at it right now is something called X. X is the variable I care about. Well, again, if we're playing the game of this big, massive variables are influenced by other variables, and we're trying to build a structure that is a DAG, right? Well, then we have certain things we care about, certain things we do not care about. X, right? The only thing I care about with x is itself and its parents. Fine. That's where, again, if we look at something like child 2, C2, right? The only thing I care about is x and then some other, what I'm calling non-descendant, right, in ND2. That's why I don't care to worry about it for x, right? There's no influence on this variable to my x. I don't need to worry about it. I don't need to use it in calculations. And that's where we start to get into this kind of mindset. Is that a question?
Yeah, we can't have P2 be connected to ND2, right? That would create, that doesn't create a cycle though, right?
P2 to ND2?
Yeah.
You can.
You can?
Right, again, think DAG, almost waterfall structure. It can't ever, right. Yeah. So in that kind of situation, I could technically have it. I'm not, for the sake of like not having it. But again, the idea here is this structure turns into what we deal with in a lot of our worlds, or in a lot of our machine learning algorithms, because what we have established is there are certain variables that I do have in space that I do not need to worry about in the given moment. Right? That's kind of the important. How dare you? That's the important part that we start to look at, right? Since it doesn't have any influence, we don't care about it. But if it does have influence, we do care about it. Why that starts to come into play is welcome. Oh, I love that. That was just a look of like, oh, math. That symbol. What are we dealing with, right? Look at all we're asking here. Hey, given the probability of just a list of variables with some assumption, all the calculation turns out to be, what's that symbol? Say it loud, say it proud. Multiplication. You're just doing repeated multiplication, right? That's a for loop where your inner variable is multiplied. That's it, right? X asterisk equal I. That's it. You're doing that. You've done that multiple times. That's all that symbol does, right? Okay, calm down. But what are you doing it to? You're just doing, hey, well, what's the probability of my variable, my given variable, being the variable I said it was, given the observation of what are the values of its parents. That's it, right? This whole shebang just turns into the same calculation I've shown you multiple times over, right? Where are you? I showed this to you. It's right here. I just didn't do it with a symbol, right? So I'm just kind of making the math, have a formal structure to it versus just arbitrarily throwing it in there. But this is the calculation that we're looking off of to find out any of our calculations. So again, we got some product based on the parents. So let's take a look at it. I'm picking one. Very simple. Here's that same structure. A influences B, B influences both C and D. I ask the question, what is the probability? What is the probability? A is true, B is true, C is true, D is true. Now, you don't have the joint probability distribution table. You don't get the thing where you get to just do the lookup, right? Because that could be an exhaustive search. Rather, I'm going to use these smaller tables and just do smaller searches. That's my divide and conquer. I still have to do them. I still have to do some exhaustive searching. But this is going to be much smaller than, 2 to the 4th power. I know that's not a big number, but right, I only have 2 things I got to look at instead of 8, right? I only have 4 things instead of 8. I only have 4 things instead of 8, et cetera, et cetera. So what am I going to do? Well, here's where it's simple mapping, right? What's the probability? What does this translate into? Before we get into the math side, what is the equivalent Bayesian network or conditional probability calculation? I'll start with the easy part. Yeah. Times the probability of B given A. Someone else. The probability of C given B. And taking it home, someone from that side of the crowd. Not D given C. What has a line pointing directly at D? B, right. The probability of D given B. Okay, well again, I've done the mapping out, and here's where the fun part begins, right? Again, I have smaller truth tables that I can refer to, and you see they're labeled the correct way, right? Oh, the probability of A being true. The probability of B being true when A is true. The probability of C when C is true when B is true, right? I'm cheating here because, I get to do the easy one. I make y'all do the hard one, such as life, right? Probability of D being true when B is true. So I take all these values, I map them out, I build that same structure, and then I'm just doing replacements, right? I'm just swapping them out for their smaller truth tables. I get my probability of 4, 3, 1, 95, and I get a wonderful magical number. Look at that. There is a less than 1% chance of this happening. Good, okay. You're all happy with that less than 1% chance of it happening? No? Well, now you get to have a little fun with yourself, right? Now, using the same table, but now I'm just going to throw in some little false statements. Answer out some questions. With that out of the way, let's see where we are on time. I will give you 12:29. So I'll give you 6 minutes to do some math. And we'll be back. And we are back, ladies and... What? And we are back, ladies and gentlemen. Sorry. Hey, look. Live studio audience. Sometimes you got to take multiple takes. Anyways, my point being, let's see how we did. Ba-ba-da-ba. Shaka-da-ba. Viewing the sheets. Yeah, so if we're looking at this overall, again, some of them being generous, right? It's just the simple mapping. So a little bit, be mindful. You may have, you went a little too fast there. So just kind of take a little, again, this is why I do these things, right? Take a second, assess the situation before you immediately start running through your math equations, because that's where I know I get tripped up as well, right? I go too fast. Slow down. So again, as we're kind of moving through these, most of these are just, hey, can you look at the same thing going on? But then we get into the math side of things. And right now we're starting to get into some funky different calculations going on here. Oh, man. I'm going to assume that one's just off by 1. But since I'm seeing so many, I'm going to make the assumption it's the 164. Okay, fine. If we're looking at that calculation, right, again, which one are we dealing with? We're dealing with, that was a false true, right? So we're looking at this calculation right here. Okay, well, I mapped that out. It's over on orange here. I don't know if chat can see it, so I'll at least bring it slightly closer. So if we're looking at that, again, what is that? 0.407, power of calculator activates. Once again, we're computer scientists. We don't do the math. We build things to do the math for us. 0.7 times 0.4 times, what was the next one? 0.6 times 0.98. 98. So again, be mindful, take it a little slower, because as I'm looking through these, if your math connections were slightly off, this is where that one's the same calculation, but something a little funky here. So kind of double check your work, double check your maths a little bit going on here. I'm going to assume, again, that one's probably a little off by one. Boom. And here we are. So a little bit lower on that last one. But again, take it. It is simple math, but think about it in the sense of that's where they get you, right? That's how I look at these types of calculations. Simple math, but it's the steps. Somewhere in the steps that'll get you with your mistakes. Because that's, again, it doesn't help that I decided to flip these. They're no longer true falses, they're false trues. I know, I'm a monster. Right? Sometimes, hey, again, we got to be mindful of what we're looking at. So if it changes, right, slow down. But again, why do we do this? Why do we focus on this whole calculation process going on here, right? The big idea is that this is meant to help us reduce the number of variables we need for making assessments, right? Again, think we are in still sort of the section before machine learning. Wednesday we'll talk machine learning, but we're still kind of in this area of what we call uncertainty. I don't have a direct answer. I only have confidence levels, right? There's no proof anymore. I can't prove the curiosity killed a cat, definitely, but I can show probabilistic reasoning, from these things. And so let's arbitrarily say I've got some 4 random variables. I got it's cloudy, sprinklers are on, raining, and then wet grass, right? Again, the idea would be that I could map out every possible calculation of all these different variables. Again, this would turn into 32 or 16. Right. 16 if I'm doing the calculation, right? What's the probability of a wet grass, right? I don't know what it is outside. You've done this before. Who here checks the weather before they walk outside? You've done this, right? You don't know what the weather's like, but you gather information beforehand, right? And ignoring the people who just walk outside for a second and be like, oh, okay, coat day. North Carolina, and we're in that weird state. I get it, right? But, hey, I don't know what the weather's like, so I'm going to make assessments. I'm going to grab some observations first, and then that same kind of notion, right? So if I wanted to find the probability of wet grass, well, here are my observations. Is it cloudy? Are the sprinklers on? Is it raining? Given these, right, what I'm trying to get at is to find the probability given other observations. Think about how many things I have to do calculation-wise. I've got to do a large number of calculations. I got to do essentially a brute force, right? I know W, so I can truncate that one. I still have to traverse every single one of these until I get C, S, and R at their values, right? So I have to kind of do the traversal to find that. The problem with that is, again, this turns out to be a large number. 15, not large, decently large. When we start to add in this notion of influence, though, right? Now we're starting to say, hey, well, if it's cloudy, right, you don't run your sprinklers because that produces mold, and you don't want mold on your grass, right? Likewise, if it's cloudy, well, clouds indicate rain. It is not going to rain today. How do I know? It's not cloudy. What does that mean to the grass? Well, if it's not going to rain today, potentially you're going to have dry grass. This is why my dad installs sprinkler systems. I may know a thing or two about a sprinkler system. If you're interested, I can give you his business card, and you can all pay him large amounts of money and not let him retire at the age of 65. My point being, right, okay, again, I have now a connection going on here. Because I have the connection, again, think Bayesian network. That header is saying is parameter reduction, right? I'm trying to reduce how many possible calculations I had to search through when I'm making an assessment on something like wet grass. What's the probability of wet grass? when we deal with this, when we're dealing with the Bayesian network, now we're no longer dealing with that big, massive calculation, right? We're not dealing with 2 to the k minus 1, right? We're just going to be working with, in this case, n times 2 to the power of k. Oh, right, different k, right? N, number of nodes, times 2 to the power of k, where k means a different thing. In this case, k references which node has the most parents. That's it. That's how many calculations you got to deal with. Just whoever has the most parents, that's your biggest parent, influences. That's it. What that turns into is, again, we start to see smaller calculations. I know, again, 15 to 9 is not a major difference, right? So let me show you an example that's different, right? Now, let's try and make an assumption of an n of 200. There are 200 variables in my equation suddenly, right? So 2 to the power of 200. Who does that math real fast, right? You know that's a big infinite number, right? Too big. You do that, I didn't even put it on here, right? It's a scientific notation that we all agree is just a big number, right? Too big of a number. Bayesian network, right? Oh, I'm still working off of that 200, but let's assume that k, right, this idea that there is just one node that has multiple parents, one node that has a maximum of 5 parents. So one node is influenced by exactly 5 things, right? Okay, fine. That's just my calculation. Again, I said a Bayesian network parameter reduction turned out to be in my 200, 2 to the power of k, not 2 to the power of n, k. 200 times 2 to the power of 5. That's a small reduction. Big number that none of us wanted to calculate? Itty bitty number. Look at it, 6,000 off of that many possible variables. This is why we were using we were using these so much, right, before we got into, neural networks and machine learning, right? Because that's a very small calculation. Again, if we're trying to deal with scale, I'm willing to make these moves because this is 6,000 iterations. You can do that. You've built things that run longer, right? That's why it was a powerful tool. So much, much less. So now as we're starting to kind of look at this, right? Okay, we see the merit. We got the calculation. But that's such a small number, right? You did the calculations. You notice every single one of them tiny, right? Tiny. That's because it was only a part of the question, right? Why did I focus in on this? Well, again, think about what you did with conditional probability. What did you do? What do you do in conditional probability? You did it for a midterm. Please tell me you didn't already throw it out, because we're still using it a lot.
What we were doing is if there was like a or something there, sorry, not or, like a pipe or whatever it is. We were trying to check whether we're trying to check on the top where all of them are met, and then we're dividing that by on the right side of the pipe the total probability.
Yes.
I can't even explain it.
No. But you did a great job, right? That you were correct, right? We make an assumption. So we, again, this was just one piece of the puzzle. When we deal with the assumption, right? It's everything that was presented over just whatever we have observed. It's a division, and we're essentially asking, given this value, let's assume that this is the denominator, right? How much of my assumption takes up this number? So we're doing very small floating point math, which again is a challenge point for computer science because we're limited to a 64-bit processor, but that's where these things come into play. So now we're looking at something. What happens if I only have some of the observations? I have a simple question here, right? What is the probability that A is true? Again, it's the same calculations going on here, but what is the probability that A is true given I only have some observations? B, let's assume, is some kind of, I use an analogy of like medical diagnoses because, all right, well, what's the probability that some medical condition is true based on the patient's observed symptoms, right? They came in with swelling and a fever. Those are the things I do know. What's the probability of pneumonia? Well, again, notice there's things that kind of are hiding, or not hiding, but I'm not really addressing. I can't immediately test for or observe because, either they're invasive from like a surgery perspective, or expensive from a test perspective, or, expensive from a time or cost perspective on that. But again, I don't know B. So what happens? Well, again, I'm going to do the same structure that we saw beforehand, right? I'm going to assume all of these things are true, add them together. Then I'm going to divide by only the things I know exist, or I know have, in this case, true values. So, again, that's conditional probability in a nutshell, right? I'm not doing anything different here. Right? I just changed the variables. That's literally the same slide. I just changed y into two variables. I changed x into a. Good? We're good so far? No mind blown yet? Mind is a little tired, apparently. Right? So again, we're just kind of doing that same summation over again, right? You did this. This was one of your questions on your midterm, right? I know. I've graded. We're still on grading. We're almost done. We've graded them, right? So we're going to do that same kind of approach. I'm going to do the denominator first. Why? Get all the calculations out ahead of time. Again, I get to do both of these. You have to play the game of like, which one's easier for me. But again, right? I'm assuming this bottom probability. I'm saying, well, let's assume C is true and D is true. We are dealing with a Bayesian network. What does this translate into? What is the calculation? I'll use this one. Given what we've seen and what we see on the board when it comes to the graph, come here. Don't you dare fall. Right? The probability of C comma D is going to equal what? I'll give you a hint. It's two things. It's a thing times a thing. It's a thing. Well, we don't have those. But what do we have? Remember, look at what we've got. So you're on the right track. That's why I don't want to pull away from you quite yet. It's probability of C given B. It's the probability of D given B.
Is that both true and false?
Yes. So that's where, again, we're going to start to plan this out or fan this out a little bit more as we go. But, again, I don't have probability of C, but I do have, again, since we do have influences, right, it's C in respect to B. Well, again, okay, I don't have B. B's not observed.
The funky math, can't we, where we basically backtrack to find the probability of
can, but you don't need to. Now I move to the next slide, and I'll show you essentially what happens, right? Again, I have my calculations, I have my game plan, I know that these are the values I need to work off of. But I clearly don't know what B is, right? That's the important part. That's where we start to map it out, right? So it becomes every single one of the calculations that I don't know about. So, again, probabilities of A. Well, let's assume that A is true. Let's assume B's are true. Let's assume when B's are false. Here's where I see a lot of hiccups from students. Treat this, when you start to have to write these out and do the calculations by hand, I don't know, on a final exam, in a lecture exercise 5, right? Do a binary structure with your calculations, right? Think about it, no different. A, B, well, I'm going to start with all of them being true, right? C is true, D is true. I'm going to assume B is true. I'm going to assume A is true. Now it's flipping your bits. I don't flip these because C and D I know are true. Those are observed. Those are fixed. But now when I go with my A and B calculations, as I have to write them out, start playing binary. Right? I'm only going to give you like a true-false value thing. I'm not going to give you anything weird and funky. But you can see, hey, boom, right? That's going to allow me to do when A and B are true, when A is true but B is false, when A is false but B is true, when both of them are false. That's exactly what I have on the board, right, at the same time. Look at the structure. That's what you're kind of going from. So just to keep on going, I map these out. This is where, hey, look at the calculations. As I start to build these out, you're seeing it's going to be the same value, right, that I have over here, right? What we are going to be building off of this is, okay, well, hey, here's the probabilities of A, boom. Here's the probabilities of B, boom. Here's probabilities of C, boom. Here's probabilities of D, boom. Okay? You know this math. You have these mappings. You know you can, this is the lookup all of a sudden. What's the probability of A being true? Like that. What's the probability of B and A being true? What's the probability of B being true when A is false? There. And what am I doing? I'm doing a bunch of multiplications, and then I'm doing a bunch of additions. So take that probability, do its math, add it to the next batch, add it to the next batch, add it to the next batch. I run through each one of these calculations. So I get, boom, that first calculation, that second calculation, third, fourth. Good? Following? Bueller? You get all of those calculations. Looks, again, they're very tiny. But, again, tiny decimal points added together become bigger decimal points, right? Yes, you can see the 16 is going to be really helpful here. But that 0.3%, that 5%, that 1%, add all those together, we start to see something form. So we calculate that out. Boom. You can see what we get as our final calculation for the probability that C is true and D is true turns out to be roughly 24%, 23.5% if you want to, mince words of like rounding or truncating, apparently. Who's the truncator? Look down in shame, truncator. Now what? Okay, I've tackled the denominator, right? I have mapped everything out. Now what am I doing? I'm just saying, well, hey, given that I know the denominator, how much does this take up of that whole pie, right? How much does knowing A is true take up to that whole pie? This is where we get a little bit of a luxury, right? I only have to worry about when A was true. This is why I follow this kind of structure, right? Because what that's given me now, just so everyone can see it, is I can just ignore or scratch out or do whatever I need to do on the variables I don't care about, right? I've already done these calculations, so I don't need to do them again. So, when I think about the denominators, because map out everything, and then I'm just grabbing the ones I need left. The other way is do the numerator first and then finish with all the opposites. Both work, but it's more along the lines of make sure you have the right number of calculations. When I see your Piazza posts and office hours, oftentimes it's you didn't do the right number of calculations. Should be a power of 2. And there's a good hint. Just you should be doing a power 2 for your lecture exercise. Anyways, you've done them. Map them out. Boom, there they are. I'll calculate them again. So in this case, there's that 16, but there's that 1 as well. And so what happens? Well, again, if we thought about it, I have 0.235998. I'm now asking, essentially, the question of, well, what was the probability that A is true in the case that C and D are true, right? Again, I only have these 2 observed variables. I have a patient that has come into the OR or the urgent care. They are exhibiting this symptom and this symptom. What's the probability that they have a condition? Okay, well, again, I can do the math. I can run through these whole calculations, and what I should be able to see here now is the probability that A is a specific value given my observed evidence. So I take those calculations, I add them together, and what we get here is a 17604. So what do? Not sure if this is an issue, but the mic seems randomly quiet.
That's because it was off, Sonia.
I apologize. But I do the calculations, right? Again, I go in, I map out the division. So again, here's my A, C, all that. I did the calculations. I mapped it out. What's that roughly translate into? The probability that A is true, given that C and D are true, is, roughly speaking, 75%. Bam! Look at that. We've built out a case that we have now. I don't have an exact answer, but again, we're thinking about this from the artificial agent's perspective. I have a probability. I have a confidence of saying that A is true at a pretty high threshold, right? Again, if this was a spam filter, right, which we'll see in 2 weeks when we talk natural language processing, right? You'll see the same thing, right? You'll see these calculations, and that's where you don't send, you don't tell someone if they've got an email, or you put it in the spam folder. We don't have time for the group exercise, but what I am going to at least do, because I technically have dropped it from the class, is I'm going to at least touch on. So I got rid of this. Deseparation, I'm dropping it so that I can give you this new lecture, which you'll get to see next week. So, spoilers. But deseparation kind of pans a little bit more into this structure, just so you can kind of think about it. So this is what problem set 6 used to be, right? This notion of, well, hey, let's look at some kind of Bayesian network like this, right? I have observations, an X-ray, bronchitis, right? I very quickly can observe that by, tongue depressor and looking in your mouth. Cancer, very difficult thing to test for, very invasive. But what's the cause of those cancers is also something that we have to be mindful of, right? You don't just magically produce it. So it could be additional observations or things that I might be able to see. Those things can populate out, but deseparation sort of gets into this weird, funky world where you now have to start looking at the patterns. So I'll just kind of refer to, I'm not going to try and lecture on this because it's a lot, But this is where we get into the notion of like trying to identify when I do and do not need to do a calculation, right? I'm showing you, if we kind of do a mapping to what we did today. I told you to do every mathematical calculation. Doesn't seem like, well, what's the difference between conditional probability and Bayesian? Oh.
Bayesian just requires extra steps.
No, Bayesian requires extra. I'll say Bayesian requires extra steps, but to reduce the number of steps. So again, because in this case cancer comes into play, in this situation, well, I have to include the probability of bronchitis on the X-ray. Is that a question?
No. Can you release the slides even if you put like a header like not on exam?
Yeah, sure. Yeah. It goes into weird, wild stuff, but you can see it gets into some ugliness. There's a whole shebang about like how you do calculations. Again, this will no longer be on the lecture, so that problem set example part doesn't exist. I will post this so you can have it as a reference. And once again, Sonia, I apologize for not having my microphone back on. But with that, ladies and gentlemen, I'll see y'all on Wednesday.